Alrighty, so we were just talking about collinearity, and you should go read that section on collinearity in the text. When you get the summary of your model, we talked about the different estimates, the intercept and the three slopes. You also get these things at the bottom. You get a standard error. Remember we talked about standard error of the estimate already? It's a way of assessing how accurate your model is at predicting the dependent variable. And in this case, the standard error is 324.9. What are the units of that? 324.9 what? Does anyone know? Yeah.
Grams?
Yeah, grams. It's in units of the dependent measure, which is body mass in grams. So this says the standard error of estimating body mass using these three variables is 324.9 grams. Is that good? Is that bad? When I looked at the data, these penguins weigh like 3,000, 4,000 grams. So this is about 10%. I don't know, is that good or bad? It's about 10%. This thing called multiple R squared, 0.5. Remember in bivariate regression we talked about R squared as a measure of model fit. It's the amount of variance in the dependent variable that's predicted by or accounted for by variance in the independent variables. Same thing here. This means that 50.82% of the variance in body mass is accounted for by flipper length, bill length, and bill depth. We also get a p-value. On the very bottom, we get an f-test and a p-value. This is what we call a test of the model as a whole. It's an overall test of the model. And in bivariate regression, we saw how this test was the same test as the test of the slope in bivariate regression, when there was just one x variable. But now we have three slopes. And so now this test is different. It's not the same as any individual test here. This test at the bottom, the test of the model as a whole, it's now a bit of a sort of an overkill of a test. It's sort of an extreme test. It's a test of whether all of these slopes together are zero or not. It's a test of whether any of these things matter or not. It's testing this model with three variables in it versus a different hypothetical model with zero x variables in it. And it's saying, does the model that has three variables in it, is that a better model than a model with none? And yeah, the model with three is way better than the model with none. So it's a bit of a weird test to do, actually. Although, if this test was not significant, that would be a big red flag. It would mean that adding these three variables in your model is not really any better than leaving them out. So that's what that test at the bottom is. We're going to talk about what adjusted R squared is shortly when we talk about refining the model. Yeah?
How do you conceptualize a model similar to?
Yeah, so the question is, how do you conceptualize a model with no variables in it? Anyone have an answer to that? What would a model with no x variables in it look like? What would the equation be? Yeah. Yeah, it would just be a horizontal line. And so the equation would be y equals beta 0 plus nothing. Just beta 0, and just have an intercept. And so here's a question. You've got these 150 penguins. They each have a body mass. So you've got 150 numbers. If your model was y equals beta 0, what would beta 0 be? What would your estimate of beta 0 be?
It's the mean of the data set?
Yeah, it's just the mean. It's just the mean of the dependent variable. So it would be a horizontal line going through the mean of the dependent variable. So a model with nothing, with no x variables, would just have an intercept. Yeah.
So just wondering, when it comes to that p-value, that's more of a holistic one of all the variables, right? So what happens if within the individual variables of x, right? And I think this goes back to a bit about the whole linearity thing. But what if one of them was like very non one statistically significant, like for the p-value of one individual one, but then the other ones were also statistically significant that it ends up pulling
Yeah.
the overall.
Yeah, so the question was, if you've got several x variables and one of them turns out to be not significant, but the other ones are, would that sort of pull the whole model towards this being still significant? Yes, it would. And that's okay, because this is a very coarse kind of a test. It's a test of whether including all this stuff is better than including none of it. It doesn't distinguish between which of the stuff needs to be there or not. And that's what we're going to talk about now, is refining the model. How to tell which of these things should be there or not. This test tells you that yes, including all of them is better than including none. But if you want to go a step further and say, well, okay, that's nice, but which of these really matters? And which of them can I take out? Then that's what we'll talk about next with refining the model. And adjusted R-squared is one of the ways that we're going to look at that. Let me skip over this. You can look at this on your own. It's just a way of plotting the coefficients of the model. We don't need to talk about that now. So refining the model. We have our full model. It's full because it has all of the x variables that we thought might be useful. But is it the best model? Do we need all three of the variables in this case? And a sort of mathematical way of asking that question is, do all three variables explain unique portions of variance in body mass? Do they all do independent work in the model? Or do some of them overlap with each other? If two x variables are highly collinear, then they're kind of doing the same work. If two x variables are not related at all, but they both help you predict a dependent variable, then they're both doing work and they're doing independent work. So that's the sort of general concept of refining the model. The other reason to refine a model, apart from the mathematical reason, is just a principle of parsimony in science. And parsimony means simple explanations take priority over complicated explanations. If you can explain a phenomenon out there in the world, phenomenon, I always get that wrong. Phenomenon is singular, phenomenon. If you can explain a phenomenon out there in the world using a simple model that explains it just as well as a complicated model, then let's just use the simple model, unless there's a specific reason to use the more complicated model. So we should, in science in general, we should prefer simple explanations to complicated explanations. Okay, this is how I conceptualize the sort of overlapping pieces of work in a multiple regression model. Imagine this big circle is the total variance in our dependent measure, y. It's the total amount of variability in the data that we're trying to predict. Let's say we start building a multiple regression model by first adding a single x variable, x1. So now this blue shaded region is the portion, it's the component of the total variance that's explained by that x1 variable. Is that a lot? Is that a little? Is that a big blob? I don't know. It's a blob. That's the amount of variance that's explained by x1. And this other variance is unexplained. So this other variance would be the residuals. This blue blob would be the sum of the squares of the model, and the white space would be sum of squares of the residuals. What happens if we add a second x variable? Well, this could happen. If we add another x variable to our model, it also explains a chunk of the variability in the dependent measure. But there's some overlap with x1. Some of the variance that's explained by x2 is also explained by x1. Some of it's not, though. So now that we have two variables in the model, this little crescent out here in light, what is that, cyan? That little crescent, that non-overlapping part, is the unique. It's the unique variance in y that's accounted for by x1. This purple crescent is the unique variance in y that's accounted for by x2. And that blue region, that's the overlap. That's the shared variance. That's the variance in y that's accounted for both by x1 and x2. Now what happens if we add a third x variable, x3? So now our model is y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. x3 is this yellow one. And so it overlaps with a whole bunch of stuff, right? It overlaps with x1 and it overlaps a little bit with x2. But this light yellow crescent on the edge is now the unique variance in y that's accounted for by x3. We still have this purple bit, the unique variance in x2, the unique variance in y that's accounted for by x2. Now look at the unique variance in y that's accounted for by x1. Right? At the beginning of this exercise, x1 explained a lot of unique variance when it was the only thing in the model, right? Once we added x2 and x3, they both overlap sufficiently with x1 that now we only have this little tiny bit here at the top. That is the only chunk of variance in y that's uniquely explained by x1. That's a pretty small amount. So now the question arises, do we really need x1 in the model? It's not doing much work. If we took x1 away, we would explain the same amount of variance except for this little bit here. I guess there's a tiny bit here as well. Right? Imagine this bit was taken away. Would the model be that much worse? Probably not. But this kind of raises another question. If we can just keep adding variables and gradually fill in the overall variance, even if they overlap with each other, what's the problem? We're trying to predict penguin weight using fill depth, fill length, flipper length. Why not just collect like another 55 variables and just throw them all in? Why not collect 100 variables and throw them all in? Each one is going to occupy some portion of this. Why not just cover the whole space with as much as possible? What's the downside?
Has they mentioned about the concept of collinearity?
Yeah, there's a concept of collinearity. So some of those might be correlated with each other, which would make the model a bit unstable. That's true.
And it also towards the distinction of each of the vectors, their unique contribution to the
Yeah, and if there's collinearity, it kind of blurs the distinction about their unique portion, their unique contribution. That's certainly true. Yeah.
To do with errors, like if you add a lot of them, like 100 different variables, will get all compound.
So if you add 100 variables, wouldn't that somehow compound the errors? It actually turns out to be the opposite. The more variables you add, the lower the error will be. And so like mathematically, you could add 1,000 variables and you can get your error down near zero. Mathematically. But there's a different problem. Yeah.
It kind of just doesn't really mean anything anymore. Like you don't even know like what. Like you can't report anything. It's like, wow, these 100 things caused this to happen.
Yeah, that's a good point. So the point was, even if you could do that, it kind of, you end up in a situation where you can't explain as well what's going on. Because you have these 100 variables that each do a little tiny little bit of work. And they each have a slope. But if you were then asked, well, how does your model actually work? Like, what concepts is it using to make this prediction? What's important, what's not? You sort of have to say, well, I don't know. These 100 things help you do it, and they all matter a little tiny bit. I don't know how. Incidentally, that's the issue with ChatGPT, at least at present, is that it's a model. It's not a linear model. It's a nonlinear regression kind of a model, but it is essentially the same concept. You have an input, and based on the input that you give it, it's kind of predict an output. It happens to have something, I don't know what, some number of billion parameters. So it has beta 0, beta 1, up to like beta 3 billion. And each of those parameters is like a slope on different kinds of input you give it. And so this is a big issue with ChatGPT. You can seemingly do all these things, but nobody has any clue about how it's doing it, what matters, what doesn't matter. Is it actually forming a concept of anything, or is it just doing pattern matching? When you have so many variables in the model, and it's just a statistical model, which it is, it's hard to interpret, yeah. But I was thinking of something different. Yes?
Is it because whenever we add one word predictor, then we're using like 1 degree of freedom?
Yeah, exactly. It's about degrees of freedom, and there's a little hint, because I wrote in this circle. Is it worth 1 degree of freedom? Question mark. So each time we add a variable to the model, we are spending 1 degree of freedom in order to do that. So you can think of degrees of freedom in the linear model like a little bag of money that you have, a little bag of coins. And each time you add another variable to your model, you have to spend 1 of your degrees of freedom. And you only have a certain number of degrees of freedom in your model to spend to begin with. And does anybody know how many? Like what dictates how many degrees of freedom you have? Yes.
How much data you have?
That's right. How much data? It's how many observations you have in your data set. If you have a small data set with 10 penguins in it, then you have the number of degrees of freedom in your model is 10 minus the number of parameters you have to estimate. So if you have an intercept and 1 slope, then you only have to spend 2 of those 10 degrees of freedom. If you have an intercept and 11 x variables, then you have to spend 12 degrees of freedom, but you only have 10. So you can't do it. And I'll show you why mathematically. So the test of the model as a whole is an F test. And I think you looked at an F test last term within ANOVA. It's the same concept as a t-test. It's a ratio where on the top you have mean squares for your model, and on the bottom you have mean squares residuals. The mean squares model is equal to a ratio of the sum of squares model divided by degrees of freedom model. The bottom, mean squared residuals, is also a ratio, sum of squares residuals over degrees of freedom residuals. If this is a little fast, don't worry, it's in the readings. So, you want a big F value. A big F value means you're going to get a small p-value, which means the model is better than the model with nothing. So we're always aiming for a big value of F. That means the top has to be bigger than the bottom. So mean squares model has to be bigger than the mean squares residuals. Sum of squares model is sum of squares total minus sum of squares, what does that say? Residuals. Sum of squares residuals is just a leftover, unexplained sum of squares. Degrees of freedom model is K, the number of X variables. So that's your spend. That's how much degrees of freedom you spend. 1 for each variable in your model. Degrees of freedom residuals is N, the number of observations, minus the number of X variables, minus 1. Anyone know why you have to do minus 1?
Is it the intercept?
It's the intercept, yeah. Because you have to spend 1 degree of freedom for each coefficient in your model. You've got 1 slope for each variable, that's K, and then you've got 1 intercept, so that's the minus 1. Yeah.
And I wonder, in terms of the degree of freedom for the model, why don't they also subtract the intercept from it?
Oh, here? No, you only subtract the intercept once, I believe, unless I made a mistake. But I'll check that after. Okay, so let's look at 2 scenarios. One scenario is you add an X variable to your model that explains a lot of unique variance. It's doing a lot of work, independent of the other things in the model. Okay, so what happens in that situation? The sum of squares for the model should go up because you're accounting for a bigger chunk of variance with the model. The degrees of freedom in the model also goes up. You have to spend 1 degree of freedom to put that variable in. So you've got a big increase over plus 1. So probably a big increase over just plus 1 results in a big increase overall. So mean squared model is increasing. What happens to mean squares residuals? The sum of squares residuals is the unexplained variance. So if you've added something that explains a lot of unique variance on its own, then the unexplained variance should go down a lot. So you've got a big decrease. The degrees of freedom residual goes down by 1. That's the degree of freedom you have to pay. So a big decrease over a small decrease, that results overall in a big decrease. So the top has gotten a lot bigger, the bottom has gotten a lot smaller. So a big number over a small number is a big number. So f has increased. So if we add an x variable that explains a lot of unique variance, then that's good for us. Our f value goes up a lot. And our test of a model as a whole says, yeah, that model is way better than a model without anything in it. What happens if we add an x variable that does not do that? It would be like, let me go back here. It would be like, what if we had x2 and x3 in there, and we're like, I wonder if we should add x1. And we added it, and it explained only a tiny amount of variance above and beyond what's already explained. Okay, so we're adding an x variable that explains hardly any unique variance we want. So the sum of squares model, the sum of squares that's explained by the model, you probably get a very small increase because that little patch that's unique to x1 now is only small. So that goes up a little bit. We have to spend a degree of freedom, so that goes up by 1. So probably if we have a tiny increase divided by a plus 1, I mean, at best, we're going to have a small increase. You might even get a decrease in the mean squared model, but at the very best, we'll only get a very small increase. What happens to mean squared residuals? The sum of squares residuals, the unexplained variance, probably only goes down a little bit. So a very small decrease divided by a decrease of -1, because we pay a degree of freedom. So probably at best that's going to be a small increase, or it might even be an increase. And so the result of that is probably no change in f. It might even be a decrease in f, depending on how the math works out. But it's certainly not going to be a big increase in f. It's going to be at best a tiny increase, or maybe even a decrease. So that test would say, no, don't bother adding that x variable. When you do, f doesn't get big enough. It doesn't get bigger enough to justify spending that degree of freedom. So when we add an x variable to the model, we pay by taking a degree of freedom. And if we're to pay 1 degree of freedom from the mean square residual denominator, take it out of there and put it in there. That's what we're doing. We're taking 1 out of there and we're adding it to there. Then to make it worth it, the x variable should explain a lot of variance, a unique variance in y. It should increase sum of squares model and decrease sum of squares residual. Those two are going to trade off. And this should get bigger, and that should get a lot smaller. If that increase in sum of squares model is not worth it mathematically, when you move 1 degree of freedom from here to here, then the F ratio is not going to get bigger enough, and the p-value is not going to be small enough, and the answer is going to be, don't bother. That x variable does not explain enough unique variance. So the way this F-test works is it really does trade off these two concepts of simplicity versus error reduction. Because for sure, 100% mathematically, if you just keep adding x variables to your model, then sum of squares residuals will get smaller. It's never going to get bigger. You're never going to add an x variable to the model and it's going to suddenly explain less. You're always going to explain more. If you add an x variable that's literally a copy of some other x variable, then it won't explain anymore. But as long as it's not literally a copy, you're going to explain something more. It might be teeny tiny, but you're going to explain something more. You might be explaining noise, but you're going to explain something and reduce the error term. So you can always reduce the error term by adding stuff, but is it worth it? That's what this test is assessing. So if we're to pay a degree of freedom, the variable that we add should explain enough unique variance to justify that. How much is enough? How much unique variance does an x variable have to explain in order to make this whole situation to be judged worth it? The answer is that there's several different metrics that people use to make that assessment. One is by looking at adjusted R-squared. And we saw that that's one of the outputs of our multiple regression summary. There's another one called AIC. Akaike is a Japanese guy that invented this metric. And so it's called Akaike information criterion. It's just another mathematical metric, kind of like R-squared. And this is what is used by default in the step function that we're going to use to refine our model. There are other ways that you might come across in your future travels. You can use p-values for individual slopes to make this assessment, should a variable be in there or not. Right? Each slope gets a t-test and a p-value. If there's a p-value that says that slope's not reliably different than 0, then you could just remove that variable. You could make a judgment that, well, that's a test, and it failed that test, take it out. You can also do F-tests of the sort that we were doing kind of by hand before. But they all share the same concept. You compare a full model containing all your variables with a reduced model in which one of them is removed. And you're making a judgment. Does that one belong in the model or not? Should I keep it in? Should I take it out? Does it matter enough or not? So the full model is the model with everything in it, all dressed. The reduced model is you take one of those ingredients off. You take the pepperoni off the pizza and leave everything else. You say, does it still taste good? No, I need the pepperoni. Take the green peppers off. No, I need those. Take the onions off. Well, that's fine, I don't really need the onions. They can go. Okay. In the homeworks and in the exams, we're going to be only really looking at adjusted R-squared and AIC. So the other ones you don't need to go into. We're getting on in time. How are people in terms of questions? Are there any questions I can answer based on this? Yeah. Yeah, so I took some slides today on plotting the model coefficients. Yeah, look at those on your own. They're not so critical. It's not really conceptually critical. It's just a graphical way of visualizing the slopes. Okay, how are we for time? We're kind of getting on. We're a bit slower today than I wanted to be. Why don't we save the rest for next week, and we'll look at the rest of it next week. Really all that's left is going through an example of how to refine the model using the step function. And we'll go over that next time. The last slide I just want to show you before you leave. The theme of this course is linear models. And you can think of linear models as building up an explanation of your data. You can start with nothing. I mean, we talk about a model with nothing in it as having just an intercept. We can even have a model with no intercept. Your model can be like this. My dependent variable is explained by nothing, just random variation. Random variation with a mean of 0. That's a way of saying my dependent variable is 0 out there in the population. And everything in my sample that's not 0 is just random sampling noise. You can add an intercept and say, no, my variable's not 0. It's 17. And everything that's not 17 in my sample is just random variation. Or you can have a slope. My variable in the population is an intercept plus a slope times some explanatory variable, plus random noise. That's bivariate regression. And then we can have a multiple regression, multiple x variables. As many as we want. That's a model with nothing in it. Everything is 0. And everything that's not 0 is random variation. That's a model with an intercept. Everything is beta 0, and variability around beta 0 is just random noise. And that's a model with an intercept and one slope. And then we saw, that's a terrible drawing. That's a model with one intercept and 2 x variables. And in principle, we can have as many x variables as we want. And that's a situation where all the x variables are continuous. We'll see later in the course that you can also add x variables that are categorical. And then you get ANOVA. And you can have a model with some categorical and some continuous. And that's called ANCOVA, analysis of covariance. But they're all just linear models. Okay, that's all for today. Next time we'll look at the step function.